series. Just remind you the a sequence, okay, that we talked about tonight. So we go with this example. We want to find the limit of each sequence, or determine, if you like, determine if the sequence, like give you a reminder to use these notations, determine if the sequence converges or diverges. Or sometimes they ask you to find the limit of the sequence. Okay, we introduce the sequence by its general term, if you like. So the notation is going to be, for example, if you have the an equal to the 2n plus 1 over 3n minus 5, or the plus 5, this is going to be a sequence. It's like a function, and instead of using f of x, we're just using f of n, if you like. So you just find the limit to find out whether this sequence is convergent or divergent, and goes to infinity. So there's going to be the limit of this quotient, which is a 2n plus 1, and this is 3n plus 5, when n goes to infinity. You know from calculus 1 that in the degree of the top and the bottom are the same, this limit would be the ratio of the 2/3. Or the method I talked about it the other night is VHS using the n behavior. When it goes to infinity, the top is a polynomial. So the behavior, or the limit of the top, would be the same as the limit of its leading term, which is a 2n. And the leading term with the highest power of the n, is a 3n. So you simplify that, give you 2/3. Okay, so the limit of the an, the sequence limit of the n goes to infinity, is equal to the 2/3. So this means the limit does exist, the sequence converges or is convergent. So this means if n getting bigger and bigger and bigger, all the terms of the sequence would be around 2/3. Okay, they converge at 2/3. Okay, so this sequence is going to be a convergent sequence. You have various forms of these rational functions. You may have the case that the power of the bottom is going to be higher, something like n, okay, over n cubed plus 1. When the top power of the bottom is higher, this limit would be 0. But to check it, again, the limit of the bn, n goes to infinity, is going to be the limit of the n over n cubed plus 1. The method that I suggest is the limit at infinity, so the limit of the top is like the limit of the n. The bottom one is n cubed. You simplify it first, so that you get the limit of 1 over n squared when n goes to infinity. When n goes to infinity, the bottom would be infinity. So the top is the whole. Okay, pizza, you want to divide it by infinity many parts. If you divide a pizza into infinity many parts, your share is nothing. So this would be 0. So when the degree of the bottom is higher, you can write the limit 0, we accept it right away. But this is the method to prove it. Okay, so the limit of the bn, n goes to infinity, is going to be equal to the 0, and the sequence, okay, if you like, the sequence converges. I like to repeat this, but if they ask for the limit, you're done, you find the limit. But just want to know that when we converges, this limit does exist. Okay, that's a second case, the bottom is higher. There is a third case that the top is higher. For example, if the sequence is Cn, and on the top we get something like n cubed plus 2n plus 1. And at the bottom, for example, if you get n plus 7. If the degree of the top would be higher, this means when n goes to infinity, this sequence would be divergent, okay, or divergent. And the reason is, again, the limit of the Cn when n goes to infinity is equal to the limit of n cubed 2n plus 1 over n plus 7 when n goes to infinity. Again, you can shrink it. The top would be n cubed, the bottom one would be n goes to infinity. If you simplify it, that gives you n squared. And you know that when n goes to infinity, the limit of the n squared would be positive infinity. So the limit of the Cn is not a number, or let me just say, you can say that the limit does not exist. The sequence diverges. The sequence is divergent or diverges. Okay, so we got to be careful when we get to these three cases to answer it. Okay. Now there is a tricky one that you got to be careful about it. This one is going to be used from time to time in this course. So look at this sequence. Suppose the sequence of an is equal to is a -1 to the n, and this is a 3n plus 1 over n plus 7. You see, when we get this -1 to the n, when you write the term of the sequence, you see if n is going to be equal to the 1, -1 to the 1 would be -1. If n happen to be equal to 2, -1 squared would be +1. So for the odd number and the even number, that give you two different numbers. When you want to find the limit of these sequences, you got to be careful. So you have to break it in two parts. One that when n is even, you see when n is even, -1 to the n would be +1. And one when n is what? N is an odd number. If you do this type of ideas and you be measuring in mathematics in future, we are going to call those subsequences. So we get a subsequence when you take n only to be even, and you get a subsequence when n is odd, because the term of the sequence are going to be positive, negative, positive, negative. So if we take a collection of them out, you are going to have a subsequence, not the full sequence. But if a sequence happens to be convergent, means if the limit of the sequence is 5, the limit of all the subsequences must be also 5. So if you pick two subsequences with two different limits, then this means the limit of the sequence does not exist. So for this type of numbers, you have to try it. Okay, so this is what we are going to do. We are going to break it into two parts. We say that if n is even, okay, it's going to be even, then you see what we have, -1 to the n would be 1 because it's even. And your an would be 3n plus 1 over n plus 7. And the limit of an, when n goes to infinity, we talk about it. You see the power of the top and the bottom are the same. So the coefficient 3 over 1, which is 3. Or if you shrink it, the one that I did, you get 3n over n, okay? But if n is going to be odd, if n is odd, 3, 5, 7, 8, then what do you have? You have the fact that the -1 to the n would be -1. If this is going to be -1, then your an would be what? Your an would be -3n plus 1 over n plus 7. You see? And if you want to find the limit, you see now the limit of the an, in this case, when n goes to infinity, would be the same as the limit of what? -3n plus 1 over n plus 7 when n goes to infinity. In this case, because of this negative sign, the limit would be -3. So you get a 3 and the -3 here. You get two different numbers. You see 3 is not equal to the -3. So this means the limit of the sequence does not exist. You see, I put it over here. So the limit of an, when n goes to infinity, does not exist. And the sequence converges. So you've got to be careful about this sequence. We are going to use it from time to time. Okay. So if you see this, the one that you get -1 to the n, it would be two different sequences. So you got to be careful when they take the limit. Some people, they ignore it, they don't pay attention. So I want to take the limit, I don't care about -1 to the n because it may be 1 or -1. But look at this one. Because the limit of the leftover would be 3. The limit of the leftover would be 3, then it would be quite a lot. When n is even number, this fraction is not going to be changed. The limit would be 3, even or odd number. But that -1 to the n would be +1, so that gives it 3. But it's happened to be -1. If it's happened to be odd, the power can be 1, 3, 5, 7. So -1 to the n would be -1. So you get -3. So you have infinity many of the term of your sequence converges to 3. Infinity many of your sequence converges to the -3. So what is the limit? You can't say that. So in that case, the limit does not exist. Okay, so this is one of the problems. You have it in your book, and you will see it from time to time, in various problems that we have, so pay attention. Okay, so this is one group of the problems that you have to know. The other group, I talked about it the other night. You may have to use the L'Hopital rule, okay? So these are going to be involved with the ln function or the exponential function. You have done it, but just remind you that you're going to use it again. You see, if this sequence is given to you, if this is going to be n squared over e to the n, we checked this one before. We check it for x with the L'Hopital rule. Because when n goes to infinity, this is infinity over infinity. So in order to find the limit, you have to use L'Hopital rule. But I told you the other day that sequence is not a continuous function because the domain of the sequence is counting numbers, n equal to the 1, 2, 3, 4, 5, 6. And since this function is not continuous, you cannot differentiate it. You know from calculus 1 that every differentiable function must be continuous. So if you want to use the L'Hopital rule, you have to change it to the x first, okay? So make sure to remember this one. You see, when you want to check it, you say the limit of n goes to infinity. This would be infinity over infinity. So if you want to check the L'Hopital rule, you have to rewrite it. Don't write it as an n. You will lose point on the test if you write it. It's going to be x squared e to the x. X goes to positive infinity. Now it's continuous function. You can talk about derivative. So this would be infinity over infinity. So I can use the L'Hopital rule. Differentiate. Derivative of x squared is a 2x, and derivative of e to the x is e to the x. X goes to positive infinity. That gives you infinity over infinity again. So you have to continue once more. Once more, L'Hopital rule. So that gives you a limit of the 2 over e to the x. Now we get a pizza on the top. 2 is a fixed number. The bottom one is infinity, so this result would be 0. So you go back and you write your sequence. Limit n goes to infinity is equal to the 0, and the sequence converges. And the sequence converges. So be careful. If you want to use derivative, in the case of the sequence, you must change the notation into the x, because you can talk about the function when the domain is real numbers, if you like, okay? Not just the counting numbers. Okay, so these are going to be famous examples that we're going to have quite a lot in your book. Check the assignment is 11.2. Great problems really you have over there. And these are the key one that you know that you have. For those, I gave you one the other night that you have to use Squeeze theorem. Okay, I write one more for you so that you know that. A Bn equal to the, you may have cosine of n over n squared, n cubed. We're going to see this type later on. It's a Squeeze theorem. To be able to do it, the Squeeze theorem cosine of the n is between 1 and -1. You want a n cubed, you divide by n cubed, 1 over n cubed, less than equal to the cosine of n over n cubed, and less than equal to the 1 over n cubed. That's a squeeze inequality. You just squeeze it between two functions. Now you take these limits. Limit of the negative 1 over n cubed when n goes to infinity is 0. Because the bottom one is infinity. The top one is a pizza. So you divide the pizza into infinity many parts. So your shade is going to be nothing, which is 0 that we have. Okay. And this one is also would be the same thing. N goes to infinity would be 0. Now we can relate a squeeze theorem by a squeeze theorem. The limit of the cosine of n over n cubed, n goes to infinity, is equal to the 0. Okay, is equal to the 0, and of course the sequence converges. So be ready for it. As soon as you see it, see the nature of these sequences. This is a squeeze theorem. This one over here, n squared over e to the n, ln n, you have to use the Hopital rule. The other fractional one, as you saw, is just using the idea from calculus 1 to take care of it. Okay. Now this is a sequence of numbers, if you like. So what we are going to do next? You see what we're going to be interested in. The term of these sequences that we write over here, if you change n equal to the 1, 2, 3, 4, 5, 6, you are going to have infinity many numbers. Okay, infinity many numbers. So what we would like to do is, we'd like to add these numbers together, if you like. So we would like to know if we can add these terms of the sequence. In the history of mathematics, as soon as they want to add it, group of people, they object, they object to it. So they reject the idea right away, because they said that how are we going to add infinitely many numbers? The best you can do, you can add 2 numbers. You see, look at this one to get the idea of what I'm talking about. You see, if I give you 2 plus 5, you can do it. It's 7. But if I give you 3 numbers, you see, if I want to have 2 plus 5 plus 6, for example, the way we do it, we say, oh, we do the first 2 first. You see, 2 plus 5, then 7. So 2 plus 5 is 6, sorry. 2 plus 6 is 7. So 7 and 6 would be 13. This is the way you do it. If I give you 4 numbers, you see 2 plus 5 plus 6 plus 10. So what you do the 3 numbers first, 2 plus 5 plus 6, then the 10. Okay, you already got the other one, 13 plus 10, that give you 23. So if they give you various numbers, this is the way you do it. But the question is going to be how far you can go. You see, you can only go with the finite terms, if you like, finite terms. So how about if you have to do infinity many terms? You see how we're going to do that infinity many terms. This was an open question in mathematics that, they were puzzling that I can't do it. And there were some contradictions. You see, there is something that we call it a Zeno paradox. Zeno, you can search it on internet, Zeno's. He is a famous Greek mathematician. His problem is interesting. You see, that's the foundation of what we are going to talk about right now. You see, suppose this is going to be one side of this room, and this is the other side, blackboard in the class, for example. I call it 0, 1. So I would like to travel from 0 to 1. It's easy. You should be able to do it. But at those days, they argue, they say, okay, if you want to do it, you have to go up to the, middle point. So if you go up to the middle point, this is going to be 1/2. So far you travel 1/2. So what are we going to do to the rest? We are going to do the same thing. You are going to divide this one into the 1/2 again. So that gives a quarter. Okay, so this is going to be, then you have to go, another a quarter if you like. Okay, so what you're going to do, they are divide this one into this, so that give you 1/8. So that give you 1/8. Then you just continue, keep up dividing this into the different portion, etc. You see, as you divide, they claim that you divide it into infinite many parts. So in order to be able to travel from 0 to 1, you should be able to add these numbers together. And they believe that the human being, cannot add infinity many numbers. So mathematically, they say that you never be able to go from 0 to 1 because you have to go through the infinities. That's the one we call it Zeno's paradox. But you know that we use common sense. I can easily go from 0 to 1. So that was the idea that, they wanted to take care of this type of paradoxes. This is just one of them. There are quite a lot to talk about it. So what we are going to do is we are going to define what do you mean by infinite sum first. You see, infinite sum, dot, forever. So this expression that you're adding these numbers together, dot, this expression is going to be called a series. And then we're going to check to see if we can define something that eventually give us the sum of this series. You know that from 0 to 1, the sum is 1 unit. So then later on, we are going to prove that if you go on in this format, you will get to the 1. Okay, eventually we get to the 1. And that's the role of calculus. Calculus is what? It's dynamic. You move to get it. Okay, so that's the idea of the things that we're going to do for the rest of this course. Infinite series, we call it, okay? So what is going to be the notion of the infinite series? Series or infinite series? Infinite series. So what's the definite series? We need a sequence to start with, okay? Remember, it's different from sequence. So suppose, okay, a sequence. Suppose a sequence, okay, a sequence AN is the notation that I use for the sequence. Sequence AN is given. You know that the term of your sequence will be A1, A2, A3, etc. So if this is going to be the case, and then I will introduce this one, then an expression, if you like, for the time being, an expression of the form, this form, the first term, the second term of the sequence, the third term of the sequence, and going forever to the AN, like the one that I did over here. Dot. This form that we shrink it in this format, we write sigma form, okay, sigma of AN, n from 1 to infinity. It's the same thing, means you replace n by 1, that give A1, then sigma means plus, then we get the A2, A3, forever. Okay, the expression of this form is going to be called, an infinite series, an infinite series. So it is in fact the sum of the terms of the sequence AN that's already given to you. Okay, so this is going to be called infinite series. And the idea is to find it, those sum. And now, since it's infinite sum, we can only add, remember, we can add only finite sum. 2 terms, 3 terms, 5 same n terms. So we're going to introduce that terms. So the other expression that we are going to use is going to be this one. So the other notation is going to be, we are going to suppose It's going to be over notation. Suppose S1. S1 means sum of the first term. S1 would be A1. Okay, this is going to be 1. Then we introduce S2. S2 means sum of the two terms, A1 plus A2. Then S3 would be sum of the three terms. Okay, and in general, if you talk about Sn, Sn is going to be sum of the n terms. So Sn would be A1 plus A2 plus A3 up to the An only. Or in sigma form, it's going to be sigma of Ai, for example, I from 1 to n. Okay, so as we talk about it, we are able to find the finite sum. This is the finite sum because I end up with the n here. But the series that we talk about it is infinite sum. Okay, that would be infinite sum that we're going to have. And so I told you that we are interested in defining that infinite sum that we are going to have. So if the series, if this is going to be the sequence AN, this is going to be a series with the given sequence AN, and this Sn is going to be called, if this is going to be called Sn, Sn is what? Sn is called the partial sum. Partial sum of what? Of n terms. Of n terms of the series. Of the series. So for each series, there is a sequence that the series would be introduced by. Then we can create this, S1, S2, S3, Sn. And just note that Sn is going to be a sequence by itself. Okay, note that. Note that the Sn is a sequence. It's a sequence of numbers. It's a sequence because the first term is going to be A1, S2 is going to be A1 plus A2, etc. Getting those numbers. Okay. Remember, we are looking for something to define to get that definition of the infinite sum. So this is going to be the definition that we're going to have. If this sequence, you see, now when it's a sequence, we are in the sequence mode, we have all the information. If this sequence Sn converges, if the sequence of the partial sum, if the sequence, okay, sequence Sn is going to be convergent, means you got the limit. Okay, convergent, and the limit of this sequence, limit of Sn, when n goes to infinity, does S exist and is equal to the S. And then we say that if it's going to be the case, then the series that we have, the series, if the sequence of the partial sum converges, then the series sigma An n from 1 to infinity, the infinite sum, okay, is said to be, if this is going to be convergent, then the series is said to be, okay, said to be a convergent series, a convergent series. Okay, convergent series, and in this case, and that S, the limit of the partial sums that I introduced over here, and S is going to be is going to be what is the sum of the series, is the sum of the series. And in this case, we write, okay, if you can find this sum, so you write that sigma of An, n from 1 to infinity does exist and is equal to the S. You see, this is how we nicely solve the problem that I talk about it for you. So the problem of you cannot add infinity many numbers together, we say, oh, we are not going to do it. Each time you add a finite number of the terms, you are going to introduce one term of a sequence. So this sequence, you see, if that sequence converges, then we say that the infinite sum, we say that the series converges. And as you can see, it's like taking the limit of these when it goes to infinity, really, because it's going to be like the S that we talk about it before. I can write it down again, so you just agree with this. Okay, so you see, look at this one. If you want to compare it, this the thing that I did or we did over here, again, you see, note that, look at this one. What you have the limit of Sn when n goes to infinity is equal to what? Is equal to the S. Substitute for Sn. What was the Sn? You see, this is limit of n goes to infinity. What is Sn? Sn is sum of the n terms, sigma of ai, I from 1 to n equal to the S. And that was A1, A2, A3 to the AN. So this means this, like when it goes to infinity, this would becomes the infinite series, sigma of AN, n from 1 to infinity, and that would be equal to this. And now we say that the series converges. So with this definition, we take care of that paradox that I talk about it. But the difficulty is going to be how we're going to find this. You see, this is easy to write. But the question is, if I give you one, can you do it? You see, can you practically find the Sn? Because if you want to check that infinite sum, so you have to find the Sn first. And that's very difficult. It's not easy to find the Sn, and it's not easy to find the sum of the series in general. But most of the time, it's important for us to know that this sum does exist. We don't care about the actual value, but we do care that if it is possible. You see, most of the time, it would be enough for us. It's possible, then we can estimate it. So what we are going to do in this course, or for the rest of the course, we are going to check the conditions that enable you to predict whether the Kevin series is convergent or is going to be divergent. We are going to have a set of theorems, okay? The set of theorems that enable us to, at the end, quickly tell us, whether the series converges or divergence. We're going to call them convergent tests. There are going to be quite a lot, but we are going to nicely introduce them for you step by step, and I will show you how we're going to get over it. And quickly, when you see it, really, you should feel that whether this series is going to be convergent or divergent for, in a couple of 2 weeks, if you like, or 3 weeks. So the next step is going to, as I told you, how we're going to do it. Okay, I give you a sequence. Can you just move the one that I did over here for you? Form the Sn. Find the limit of the Sn and goes to infinity, call it S. If you can get S, you go back, say, oh, this is the sum of the series. Now, how are we going to do it? It's not easy. There are a couple of cases it's going to be possible. The most popular one is going to be called geometric series, quite important one. With this geometric series, there is the method that you can learn calculus to. You don't need anything else. You can connect, I can connect anything to the geometric series. So such an important object or subject. So make sure to quite understand it and be ready to use it, okay? So it's kind of an example, but really it's not. It's kind of theorem, if you like. But I write down as an example so that you know that this is it. It's the one that you have to know it. What is geometric? That's a tool. Geometric series, the most popular series in calculus or in mathematics, really. What is geometric series? You may know geometric progression. Okay, it's the same thing. So we introduce a geometric series is going to be sum of numbers. But the procedure is you start with a number, you start with the number 2. Then you multiply by a fixed number. You see, 2 times 5 is 10. 10 times 5 is going to be 50. 50 times 5 is 250, and you just keep going. So this is how we're going to introduce the geometry. You should be able to identify it quickly, and it's easy. There you are. This is introduction. Suppose A and R, they are fixed notation, are real numbers. Are real numbers. The condition that, of course, A is not 0. So A is going to be the term of the sequence. If it's going to be 0, we don't get anything. Then this is how we introduce a geometric series. You see sigma of A R to the n minus 1, n from 1 to infinity. Let's see, what does it mean? This is going to be equal to. If you replace the n by 1, you see 1 minus 1 would be 0. Anything to the power 0 is 1. So you get only A. That's your first step. Plus, if you replace the n by 2, 2 minus 1 would be 1 to get AR. The next one would be AR squared. Okay, AR cubed. And you continue. The general term would be AR to the n minus 1 and forever. Okay, so as you can see, you have a fixed numbers A, and you multiply by R, you get AR. You multiply by another R, you get AR squared. AR squared, that. Okay, if this is going to be the case, this is going to be called, okay, it's called a geometric series. A geometric series. Geometric series with the common ratio. You see, this R is going to be called with the common ratio. Common ratio R. Okay, because if you divide any of these two terms, the result would be R. Okay, so you must know that A is going to be the first term, but the R is going to be common ratio. So and this is going to be called a geometric series with the common ratio R. Okay, I give you an example. For example, you see this one. For example, say for example, if you have sigma of 1/2 to the n minus 1, n from 1 to infinity. So the first n would be 1, 1/2, okay, 1/4, 1/8, etc. So this is a geometric series. Geometric series with the first term A is equal to 1, and the common ratio is 1/2. You see, it's clear that 1/2 is the common ratio. Otherwise, you divide any of these two. You see, divide the second term by the first term, that gives 1/2. Divide the 1/4 by 1/2, that gives 1/2 again. Okay, so this is going to be a geometric series with that common ratio they're going to have. Okay, give another one. You may have something like sigma of 3/2 to the n minus 1, n from 1 to infinity. Again, the first term when n equal to 1, 3/2 to the 0 would be 1. So we get the 1/2, 3/2. Then you square it, that gives 9, 4. You multiply 3 times, another one would be what is going to be 27, 8, etc. So this is going to be again a geometric series. Geometric series with A equal to 1 and R equal to the 3. Okay. You may have some negative numbers. The other one is sigma of -3 to the n from 1 to infinity, for example. N minus 1, for example. Again, if you put n minus 1 would be 0, -3 to the 0 would be 1. Replace n by 2, that give 1 minus 3, okay, plus 3 squared would be 9, minus 27, okay, plus, that's 81, etc. So this is going to be a geometric series, is a geometric series with the common ratio, with the first term 1 and the common ratio of -3. Okay, so R can be a positive number, negative number, bigger than 1, less than 1. So that give you a geometric series. Okay, so geometric series, you start with the fixed number and you multiply by same number, just keep going, multiply by R. So you should be able to identify it, and it's not difficult to identify. Quickly you can identify it. You see, that's it, the fixed number. If you want to find the R, divide the second by the first. You see, -3 divided by 1, that give a -3. Or 9 divided by -3, that give a -3. -27 divided by 9, that give a -3. So be able to quickly identify it and get the common ratio right away. Okay. So get to know it. This is your tool for everything we want to do in this course. Now, why we like it? Because this is, in fact, one of the, let's say, the only one, or one of the one. We want to see whether this is going to be convergent or divergent. In order to do it, remember, you have to form the SN. This is the SN. You have to add only n of these numbers together and then check to see if that would take you somewhere. Okay, let's try it to see what is going to be the case for this geometric series. Okay, so I'm going to prove a theorem for you, then you can use that theorem anytime you like. So let's continue with this one. Let's suppose we have one of them. Okay, suppose, so pick one of these, geometric series that we have. Okay, so suppose the geometric series, I repeat it again, sigma of what? Sigma of a r to the n minus 1, n from 1 to infinity is given. Okay, it's ar. You continue, we get to the ar to the n minus 1, dot, is given. We want to check to see whether it's convergent or divergent. So we have to find the SN. We can't do anything here. You have to form the SN and take the limit of the SN. Okay, so there you are. Note that. Take the SN. Remember SN. Or the SN is a sum, but we stop somewhere. We stop at the n term. So it's going to be A plus AR. Okay, it's going to be AR squared. Take you to what? AR to the n minus 1. That's the SN. I want to change this one to the format that I can find its limit. Okay, I can't do it now. So I'm going to use a special trick here. The trick is going to be what I'm going to do. I'm going to multiply both sides by R. Okay, I multiply by R. Is going to be what? Multiply everything by R. So this would be AR. This would be AR squared. This would be AR to the third, etc. And this would change into what? Change to the AR to the N. Because when you multiply by R, you increase the power of R by 1 unit. Okay, next what I'm going to do is, so I just push the power, if you like, 1 unit to the right, if you like, one more. So what I'm going to do, I'm going to subtract it. Subtract these two. So what's going to be the result? Over here, I get the Sn minus Rsn. And over there, you see, these two would cancel out. These two would cancel out. These two would cancel out. And these two would cancel out. So the leftover from the first part to get the A, minus from the second part to get AR to the N. See, nice. Everything else would cancel out because they would have the same power. Okay, Libra of algebra, remember I'm looking for Sn, so I factor out the Sn. So that would give me 1 minus R times it by Sn. You can factor by A if you like, or you can leave it, it doesn't matter. Okay, let's factor A out, so that gives 1 minus R to the N. Then I'm looking for Sn, so I divided by 1 minus R. Okay, you may say R may be equal to 1. I assume it's not equal to 1 for the time being. So divide, so give me Sn equal to what? Is equal to the A times, okay, A times 1 minus R to the N. Okay, and divide by what? Divide by 1 minus R. And I assume R is not equal to 1. I can take care of that one later. Because I divided by 1 minus R, you may say, oh, what will happen if R is equal to 1? So I assume R is not equal to 1. Okay, so this is going to be the Sn. Remember, this is the sum of the what in terms of the sequence. And if you can find the limit of Sn, remember we talked about it. Sn is a sequence. If you can find the limit of Sn, then the series would be convergent, and that limit would be the sum of the series. Now, in order to get this, limit depends on what are going to have for R. So what I'm going to do, I'm going to pick some special cases. You see, if this R is going to be less than 1, if the number is less than 1, like 1/2, if you square it, that number would be getting smaller. So if R is 1/2, if you square it, we get a quarter. If you square it again, that gives 1/16. Square it again, 1/32. So that number getting smaller and smaller and smaller. So that's good for me. So, oh, if R, or the absolute value of R, let's say, is less than 1, you see if it's going to be less than 1, then what will happen? Then this limit of R to the N, when N goes to infinity, would be 0. Because when the number is less than 1, you square it, raise it to any power, that number getting smaller and smaller and smaller. Eventually it would be 0. If it would be 0, this would disappear. And this is going to be the case. So in this case, the limit of Sn, you see when it goes to infinity, would be the limit of, this is the one that we did here, 1a times 1 minus R to the N over 1 minus R, N goes to infinity. But this R to the N goes to 0. So what are we going to have? We are going to have A on the top, 1 minus R at the bottom. See, you prove one of the interesting theorems in calculus. Just want you to see it. You don't have to be able to prove it again for us. Just we need this formula. You see? Nice. So what we proved that that geometric series is going to be convergent. You see, it's going to be convergent if the absolute value of R is going to be less than 1. You see, it's going to be less than 1, then I can find the limit. If the absolute value is going to be bigger than 1, means if R is a big number, when you square it, raise it to the 4 to the 5, that number getting bigger and bigger and bigger. So the second option is going to be if the absolute value of R is bigger than 1. Okay, if this is going to be bigger than 1, then you'll be in trouble. Then the limit of R to the N Okay, n goes to infinity, would be infinity this time. This would be infinity, then you cannot find this limit. If this is going to be the case, so the limit of Sn, you see n goes to infinity, in this case, does not exist. Okay, so this limit does not exist to get this number. Okay, so that will give us, push this one so you can see it. So that will give us something quite interesting. So if this limit does not exist, so this means the geometric series, you cannot find the sum of the series. You see, if you put them together, that gives you a very nice theorem that you can use it anytime you like. What is this theorem? This theorem will tell you that the geometric series, you see this is it, the geometric series, sigma of a r to the n minus 1, n from 1 to infinity, converges if the absolute value of r is less than 1. That's it. Less than 1. Okay, and that's going to be the case. Less than 1, and in this case, the limit of the series, I mean the sum of the series, sigma a r to the n minus 1, n from 1 to infinity, in fact, is a over 1 minus r. You see, not only you get a convergent series, but also you have a formula for the sum. Otherwise, the series diverges. Okay, otherwise. So this means otherwise means if the absolute value of r is going to be greater than or equal to the 1. And the series, okay, I write down here, the series diverges. Okay, then in this case, the series diverges. Diverges means you cannot find the sum for the series. Okay, so that would be a key for many, many problems in this course. Okay, make sure I just proved it for you so that you believe it. So if the geometric, if any series is given to you in this course, you have to check first to see if it's geometric. Most of the time it is. If it's going to be geometric, you look at the common ratio, or the absolute value of a common ratio. If it's less than 1, okay, if this common ratio is going to be less than 1, your series is convergent. Okay, your series is convergent, and you can find the sum of the series using this formula. If the absolute value of r is not less than 1, means if it is equal to 1 or it's greater than 1, in that case, your series diverges. Series diverges and you cannot do anything about it. Okay, so that would be our first test, we call it. This is going to be the test for the geometric series. Okay, so I'm going to show you how I'm going to use it for the first group of the series. And that's the most popular one that we are going to have. We're going to have something like 8 or 9 of these type of theorems through this chapter. Okay, so this is how you are going to see the example. The examples are going to be, they are going to ask you to determine if the series, determine if the series converges or diverges. Sometimes they say if so, means if it converges. If it converges, if it is converges, find the sum of the series. Find the sum, means the S, sum of the series. Okay, and for the time being, you are going to have a geometric only. This is it. The first one is like the one that we start, sigma of, you see sigma of 1 over 2 to the n minus 1, n from 1 to infinity. They write it on different version, different format, but this is going to be geometric. You write a couple of them to make sure that you know it is convergent. You are not going to miss anything. You see, look at this one, solution. You have sigma of 1 over 2 to the power n minus 1, n from 1 to infinity. You write the first step because you need the first step. The first step would be out when n equal to 1. You see the top would be 1 minus 1, which is 0. 2 to the 0 is 1. So the first term is going to be, I'll write down for you, it's going to be 1 over 2 to the 0. The next one is going to be 2 to the 1. Okay, 2 squared, etc. So 2 to the 0 is 1, so that gives 1 plus 1/2 plus a quarter, etc. As you can see, this is a geometric series with the first term is 1 and the common ratio is 1/2. You see, divide the second term by the first term, that gives common ratio. 1/2 divided by 1, that gives 1/2, or a quarter divided by 1/2. So you can say that this is a geometric series. A geometric series with, okay, with R equal to the 1/2, which is less than 1. So it converges. So the series converges. You see, because the common ratio is less than 1 according to the theorem, it's going to be convergent. Okay, they ask what the sum of the series. So the sum of the series, you know that in this case, sigma of 1 over 2 to the n minus 1, n from 1 to infinity. Remember the formula is a over 1 minus r. Your a is 1, 1 minus 1, r is 1/2. So that gives you 1 on the top, and it's going to be 1/2. You flip it, that gives you 2. So this means the sum of this series, you see 1 plus 1/2 plus a quarter plus 1/8 forever. E is going to be what? Is equal to 2. Or in brief form, sigma of 1 over 2n minus 1, n from 1 to infinity is always equal to 2 to get these numbers down. Okay, that's going to be 1. So it's going to be quite interesting. It's like the one that we did. If you change, you start from n minus 1. If you start from, okay, that give me 1. Yes, if you start with the 1/2, a quarter, etc., then the result would be 1. The one that we did, the one that we introduced, that give you 1. But in this case, it's going to be equal to the 2. Okay, any question? So that's going to be the one. There is a joke about mathematicians. It's a group of mathematicians. They go to a bar and they want to have a drink together. The first one goes to the bar and just buy 1 drink. And the second one go to the bar and say, I have half of the one that the other guy have. So you get a 1/2. Then the next person goes, I have 1/2 of the other guy, a quarter, 1/2, that. At the end, they only pay for 2 drinks because the sum is going to be equal to 2. Okay, so just referring to this famous problem that we're going to have. Okay, so this is the first one. Let's get to know the geometric series. Very nice series. Give you another one. The other one is this one. Sigma of 3 to the n minus 1 again. N from 1 to infinity. Quickly, you see, it's a fixed number raised to n minus 1. That fixed number is 3. 3 is bigger than 1. The series diverges, done. It's the way quickly we can take care of it. But we can write a couple of them to make sure that you know it, or you are sure about it. So it's a 3 to the n minus 1, n from 1 to infinity. So the first term is going to be what? It's going to be 3 to the 0 plus 3 to the 1, 3 to the 2, whatever. So your term of the set is going to be 1 plus 3 plus 9, if you like, 3 squared, 3 to the third, etc. So as you can see, it's a geometric series. The fixed term is 3. Because divide these two, that give you 3. 9 divided by 3 give you 3. So say that it's a geometric series. It is a geometric series. Geometric series with r equal to 3 is bigger than 1. It diverges. And you're done. You see, when it diverges, then this means there is no limit and you are not going to worry about it. Okay, so convergent when the common ratio is less than 1, diverges when it's going to be otherwise, and then we're done. Okay, let's give you another one. And this r can be a negative number, so be careful about those type of. So it's going to number 3. Okay, number 3, you may be given something like sigma of, okay, negative 1/3 to the n, and from, sometimes they say 0 to infinity. It doesn't matter. It basically is a fixed number, negative 1/3 to the n. Negative 1/3, remember, we go with the absolute value. The absolute value of the 1/3 less than 1 is convergent. You may write it down, just to make sure. So the sigma of negative 1/3, they start with a 0. So you start with the 0 too. So it's going to be negative 1/3 to the 0. Okay, negative 1/3, negative 1/3 squared, etc. But negative 1/3 to the 0 is 1. So that gives me 1 plus negative 1/3. Okay, negative 1/3 squared, etc. So as you can see, it's a geometric series, it's a geometric series with r equal to negative 1/3. Remember, the absolute value of r would be the absolute value of negative 1/3, which is a positive 1/3, so less than 1. So the series converges. The series converges, and the sum of the series, sigma of negative 1/3 to the n, okay, to the n, and from 0 to infinity, according to our formula, is going to be a over 1 minus r. You substitute, your a is equal to 1, the first term. 1 minus r, r is negative 1/3. Remember, some people, they use a positive 1/3. No, r, not the absolute value of r. So simplify that, give you 1. It's going to be 1 plus 1/3, which is going to be 1 over 1 plus 1/3 would be 4/3. You flip it, that give it 3/4. So the sum of this series, negative 1/3 to the n, and from 0 to infinity, is equal to what? Is equal to the 3/4, and done. Nice series. We see it from now on. That is going to be such an important part for us. Okay. So far we give you one example, that, but it's not easy to find these SNs, you see. For the geometric series, it's easy to find. I told you there are only a couple of series that you'll be able to do it actually by just using these quick theorems. This is the geometric series is the first one. There is another one. There is another one. This is also very important. You have to know it by name. What is the next one? So our next example, I told you these are examples, but they are VIPs if you like. Okay, not ordinary example. Now this next one, the name is we call it a, okay, we call it the telescopic series. Okay, so these are going to be the name for this famous series. You must know it by name. That's it. Telescoping. Telescoping is like looking into the series through a telescope, and you will see what I mean in a minute. What is telescopic series? You see, these two, geometric and telescopics, are very easy to locate or identify, and you have to go for these two first. Okay, if you cannot find these two, then you go to the other theorems that we're going to introduce. At first, you have to look for this. Okay, let's see, what does it mean? You see, if you have a series of this form, if Bn is a sequence, if Bn is a sequence, then as you look at this series, you have a series whose general term is the difference of two consecutive terms of this telescopic series. You see, this is the one. Bn is a sequence to start with, but your series would be of this format, n from 1 to infinity. So for example, if the Bn is 1 over n, this would be 1 over n plus 1 minus 1 over n. So then quickly you realize that this is going to be the case. We have some series from, okay, trigonometric series, especially natural log, they are going to be in this format. That's why we need this group. So if Bn is a sequence, this format, this is going to be called, this is called a telescopic series. It's called a telescopic. That's going to be one telescoping series. Okay. Now let's see why we like it. Remember, if you want to do anything about this one, you have to form the Sn. Sn means you have to add n terms, then try to see if you can find the limit of Sn. So let's check to see what is going to be the n term of this series. Okay, so note that we are going to call this a general term if An, as usual, is Bn plus 1 minus Bn. Okay, then what is going to be the term of the sequence that you want to add them together? If this is going to be the case, then what's going to be A1? You see A1. If you replace n by 1, what is going to be the other side? The other side is start with a Bn plus 2. So if you replace n by 1, so 1 and 1 would be 2. So that you will B2. B2 minus B1. Okay, then the A2, what's going to be A2? A2 replace n by 2, that give a B3. B2 minus B2 now. Okay, if we replace n by 3, so that give A3. So it's going to be A3, which is going to be equal to 3 plus 1 would be 4. That give a B4. B4 by what? B4 minus B3. Okay, and you can keep going. You can keep going to get to the AN, the last step. If you get to the AN, so that gives us a BN plus 1 minus BN. Okay, remember we are looking for SN. For the SN, we have to add these together. So let's add them together. Okay, if you add them together, if you add this part would be A1 plus A2, A3 to AN, so that gives SN. The sum of the series in terms of the sequence, if you like. Then how about this? If you want to add them together, you see, look at this. You see this B squared, these two will cancel out. I told you, looking through the telescope, these two will cancel out, these two will cancel out, these two will cancel out, and these two will cancel out. So if you look at it, the leftover is going to be what? The leftover, you are going to get a Bn plus 1 from this last one, Bn plus 1 minus B1. That's why we call it telescopic series. When you look at it, you see you get a B1 and that Bn plus 1. These two would coincide if you like. So what we do have is we get the Sn equal to the Bn plus 1 minus Bn, you see? Easily we can find the limit of the Sn. See, as soon as you form this, depends on the Bn, sorry, that's a B1. B1. So in practice, define the limit. You see the limit of the Sn, limit of the Sn when n goes to infinity would be what? Would be the limit of Bn plus 1, n goes to infinity, and that B1 would be just a fixed number. That's it. So it depends on the Bn here, on the given sequence. If that case given is going to be convergent, then the series would be convergent. If that Bn is divergent, depends on what it is the limit, then Sn would be divergent, the series. So basically, the conclusion, you have to do it for each problem separately. You don't have to memorize anything. It depends on the given problem. So basically, you can say that the series, the telescopic series, the telescopic series converges if the sequence Bn converges. In practice, we can do it. We do this one all the time. We have to do it to see whether that series is going to be convergent or not. Okay, I'm going to be example to see how we operate with this one. Okay, very nice one. You have to know it by name. It's going to be telescoping. There is I posted one page for you on Canvas. There's going to be one page, all these theorems, we put them together. So you can keep that one, and I explain it at the next lecture. I don't have it now. Then these theorems are going to be in one chart. You can keep that chart, and that was the way you are going to know. You are going to check whether a set is going to be convergent or divergent. I just check to see. I didn't want to talk about it tonight. So that is, yeah, I'll post it first on the Canvas, then I talk about it. It's not from your book, from the other book that I teach, but let's get an example to see how we're going to operate with the telescoping one. It's very popular and very easy to identify for this series. Okay, so this is it. Again, what we would like to do is the same. These are the only two examples that you'll be able to prove the series is convergent, and we'll be able to find the sum for us. Otherwise, you can't do it. For the other one that we're going to talk about it, you just predict that the series is convergent, but you won't be able to get any limit for us. But this one is the only one. Okay, so that's why we put these two up in front, if you like. So again, the same thing. Determine if the series is convergent. Okay, determine if the series, okay, the series converges or diverges, converges or diverges, and as usual, if so, find the sum of the series. I mean, if so, I mean if it converges. Sum of the series. There are a couple of very popular ones. I'll give you two, and then we have quite a lot. Then we can practice when I post your practice test. You know that we are going to have our next target is going to be a test number 2. And I think I tried to give you that test up to that section 11.2 because this section is very dense. We better check it. So I'll finish this one after the telescoping one. Then I post a record, and I give another recording, give you more examples because we need examples to work. And then I post your practice test, and during the week, we go over that practice test. Okay, so up to the end of the 11.2 would be enough about this. Okay, let's see. Let's start with this one. This is very popular. Any calculus book, they talk about this one, and you have it also in your book, and you must know it. There are a couple of more similar to this one, so get the idea. Now, you see, you want to check ln of n plus 1, ln of n plus 1 over n. When it goes to, so seems to be very complicated series, but you see, you know that ln of a quotient is ln of a difference. So we can break it, solution, with of algebra, and this is it. You see the limit, the ln of n plus 1 over n, and from 1 to infinity, you can rewrite it as, you know that they have quotient rule, ln of n plus 1 minus ln of n. So now it's of the telescopy, because this is the difference of two consecutive terms. Okay, so what we're going to do, you're going to call this one the AN. So your AN, you have to write the details. Okay, this is going to be 1 ln n. In some, if you miss some point on the test because you didn't give us the details of the work, you have to check it. Okay, so I'm going to write a couple of terms so that you believe that this is going to be telescopic form. You see, so the A1 would be ln of, replace n by 1, 1 and 1, 2. That's it. You write a couple of terms to see how they are going to be canceling out. If you put 2, that give you ln2, ln3 minus ln2. You see, you know that they are going to be this canceling. So that to get the an, ln of n plus 1 minus ln of n. Now add them together. If you add these together, that give you Sn. And this part, you see ln2 would be cut. These are going to be out. So the leftover is going to be negative ln1 plus ln of n plus 1. Okay, you know that ln1 is 0. So you end up with a negative ln of n plus 1 only. Okay, so ln of 1 is 0. So your Sn is the same as the ln of n plus 1. You take the limit of Sn, n goes to infinity. You know that the limit of ln is, when n goes to infinity, is infinity. So the series diverges. Okay, the series diverges. And we're done. So this is one of the popular one that we have. There is another one regarding these differences that I put over here for the ln. We go for it, but you have something for the sine, tangent, tan inverse, but they give you this difference. So as soon as you see the difference here, you must realize this is a telescopic series, and then you go for it. Okay, so this is one version. The other popular one is this one that we're going to see quite a lot in future. So that's number 2. Very of these are going to be given later on. 1 over n times n plus 1. N from 1 to infinity. This is the most popular form. This series is very popular. We are going to have different methods in future to do it. But for all the other methods, we are not able to find the sum of the series. But over here, we will be doing it. Now, how are we going to take care of this one as a telescopic series? Remember those partial fraction decomposition that you did for the integrations? We do the same thing here. We break it. We break it into 2 parts. You see, this is the way you do it. Solution. Say that, note that. You can use those methods, but they are very easy. You can do it yourself. You see, it's going to be 1 over n times n plus 1. So you break it into two fractions, if you like. I mean, what we did before is we put the A1, the A2 here, common denominator, we find it, but you can do kind of shortcut for this because there is no n on the top. So when you do the cross multiplication, you would like to cancel out the n. So you put the 1 here and the -1 here and check it. You see, if you check 1 times n plus 1 would be n plus 1 minus n minus n. You see, this two would cancel out, that give you 1, which is here. So it's quick. Then I give you more, you know, that the way we can do it. So you always get 1, but if it's 2, then you divide this by 2. If it's going to be 5, divide by 5, or just use the one that you did before for integrations. You call it a and the b, cross multiply, find those coefficients. But that would be easy to do. Okay, so basically what I did is n times n plus 1 equal to the 1 over n minus 1 over n plus 1. So you see, this is the telescopic series. So I'm going to call this one an is equal to the 1 over n minus 1 over n plus 1. Write a couple of terms to see how these series would behave. So we go with the a1, which is 1 over 1 minus 1 over 1 plus 1 would be 2. We go with a2, which is replace the n by 2. So that gives you 1/2 minus 1 over 2 plus 1, which is 3. You see, you can see that they are going to be canceling in this form. You know, you don't have to write anything else. an, which is going to be 1 over n minus 1 over n plus 1. Now you see these are would cancel out. So if you add them together, these are going to be a1, 2, 3 to the an, which is the Sn. And the leftover way here is 1 minus 1 over n plus 1. You see, easy series. Take the limit of Sn, n goes to infinity. It's going to be the same as the limit of the 1 minus 1 over n plus 1 when n goes to infinity. We already talked about it. N is down the denominator, so this limit would be 0. Okay, this limit would be, okay, that's going 1. This limit would be 0. So the result would be what? The result would be 1. So the limit of the Sn is happen to be equal to the 1. So the limit of Sn, n goes to infinity, is 1. So the series converges. The series converges. And the sum of the series, sigma of 1 over n times n plus 1 is equal to 1. See, very nice method. And we get it from here. It's very popular method to be able to find. They are very popular, you know, this group that we break into part and give us a telescoping series. Okay, so these are going to be the only one really that you'll be able to take care of to get this done. So these are going to be a couple of examples of this series. Then there are some property of this series that we can use to get more information. As I told you, it's not easy for the other series to be able to find it. Easily I find the sum of the series. For the anything else that we are going to talk about it, we are going to introduce some methods to show you that this series is convergent. Means the limit of the series does exist, but we may not have the tools. Of course, tools in calculus too. You may not have the tool to be able to find the sum for you. That's why they ask you to just check to see if the series is going to be convergent or divergent. So just give us a reason. Then they may in future find a method to be able to take care of it. Okay, so that's going to be the one. Now, a couple of properties of this series that would help us, especially this next theorem, would help us to be able, we call it divergent test. to prove that a series is divergent. Look at this one. So what is going to be, again, we are in 11.2.2. It's a very dense section, very good one. Okay, so what's this theorem? Very important theorem. Okay, I call it divergent test. So this means use this test if you want to prove that a series is divergent. Why? Because of this. You see, the theorem is if sigma of an, if this series, okay, n from 1 to infinity is a convergent series. Convergent series. Okay. If the series is convergent, then the limit of this general term, limit of n goes to infinity, must be equal to the 0. That's it. Okay, so if you have a convergent series, that sequence inside, you see, we call it the general term of the series. Limit of the n goes to infinity must be 0. So why I call it divergent? Because you see, you cannot use this one to prove that a series is convergent. Because this theorem tells you that if it converges, then the limit is 0. But there is equivalent form, you see. That's why I call it divergent. Equivalently. What does it mean? You see, in logic, we say the negation of this theorem. The negation of this theorem would be if not, you see, if the limit of n goes to infinity is not equal to the 0. Then the series is not convergent, which is divergent. That's the one that you're going to use from this theorem, not this part. Okay, so if the limit of n goes to infinity is not equal to the 0, then sigma of n from 1 to infinity is divergent or is not convergent. Is divergent. That's why I call it divergent. Such a nice test. It's helped you quite a lot for future or some nice problem that you rejected right away. So that's why I recommend that if they give you a problem and they ask you to check if this series is convergent or divergent, I always recommend check limit of an. If the limit of an is equal to 0, go and check another test. Because if it's going to be 0, the series can be convergent or can be divergent. But if it is not 0, you are lucky. If you are not 0, the series is divergent. Don't waste your time. That's why I recommend to check this one all the time. Okay, quickly. Okay, and the proof is very easy. One line, let me prove it for you. See the proof? What's going to be the proof? The proof is, suppose the series convergent. You see, suppose sigma of n from 1 to infinity converges. Okay, what does it mean? Then, remember Sn that we talk about it, this means Sn, which is A1 plus A2 up to the An, okay? This Sn is a convergent, sequence. Convergent sequence. So the limit of Sn, n goes to infinity would be S. You see, that's going to be the one. Okay, also, the limit of Sn minus 1 when n goes to infinity is equal to this. Means if you add n's terms of the series, the limit is S. It doesn't matter because n goes to infinity. If you add n minus 1 would be the same thing. But what is this? You see, what is this? And the term is going to be what? Bad term. Look at the Sn. Sn is equal to what? Is A1, A2, up to the An minus 1, okay, plus An. But this is Sn minus 1. So Sn is equal to the Sn minus 1 plus An. Take the limit. Limit of Sn, n goes to infinity, is equal to the limit of Sn minus 1, n goes to infinity, plus the limit of An, n goes to infinity. And remember, this is S. This is S. And the other one is your unknown. N goes to infinity. You see, n and n would cancel out. So the limit of An, n goes to infinity would be 0. Nice theorem, you see, and easy to prove. So this means if the series is convergent, then this limit of An, n goes to infinity must be 0. You see, unfortunately, the converse is not true. So this means if the limit is 0, you cannot say that the series is convergent or divergent. But as I told you, equivalently, that would be so useful in many, many places. Equivalently, if this limit of An, n goes to infinity, is not equal to the 0, then sigma of An, n from 1 to infinity, diverges, is not convergent. Sometimes I've seen people go, when they learn all the theorems, they go deep in some very complicated theorem to prove the series is divergent, but they don't check the An first. Okay, so check the An first. Very important result. That's going to be our third test. So the first part was geometric series. The second one, telescopic one. This is, they call it, I call it divergent test, but they call it, I think the general, yes, An is the general term of the series, the general terms of the n term test, they call it. When I give you that piece of paper, you will find out. Okay, let me check it for you. See, this is the way you check. Example. Okay, we want to check, determine, if you like, determine if the series converges or diverges. Mostly I want to use that theorem that I talk about it. You see, the most famous one is this one, sigma of, you have quite a lot of these. Okay, n over n plus 1. N from 1 to infinity. You see the term of the series, the general term, solution. See your An, note that An is equal to what? N over n plus 1. And take the limit. Limit of An, n goes to infinity, is the same as the limit of n over n plus 1. Remember, we talked about it. You're shading the top and the bottom, or the degrees are the same. So it's going to be limit of n over n. N goes to infinity. You simplify it, that give you 1. So the limit of An, n goes to infinity, is 1. 1 is not equal to the 0. So the series divergent. The series diverges. And you're done. Because if it is convergent, we talk about it. The limit of an goes to infinity must be 0. It's not 0, it's not convergent. You see, very nice test. We have various other tests that you can apply to this one in future, but this is the easiest one. Okay. And you have some easy one, but useful, like this one in your assignment, sigma of ln n, n from 1 to infinity. See, quickly you have a look, say, oh, is it geometric? No. Is it telescopic? No. Did you check the an? No, I'm going to check it now. You see, this is the way you do this type of problems. You say that an is equal to the ln of n, and the limit of n goes to infinity, would be the limit of ln n goes to infinity. Limit of ln n is infinity, it's not 0. The series diverges. And then do that. Okay, as I told you, it's going to be used only when the series is going to be, okay, the series is going to be divergent only. I give you another one so that you can compare. You see, if you give you sigma of negative quarter to the n from 0 to infinity, you see this series is geometric. I just want to remind you what we did tonight. Okay, so the solution for this one is the series is geometric with the common ratio of r equal to the negative quarter. Remember the number that's going to be a fixed number. But the absolute value of r is equal to the quarter is less than 1. The series converges. Remember, geometric series is convergent if the common ratio is less than 1. That's it. That would be enough for this session. Okay. So I post that practice test for the test number 2. Then I will post another recording for you, just more examples. And I give you one more example in advance. There is something we call it P-series that will help us quite a lot and to get to know this, okay? We don't want to rush it, but at the same time, we have quite a lot to cover. But get the series if you want to be successful in Calculus 2, Calculus 3, or any others, because this is the foundation of science, really, or the application problems. So let me know if any difficulty. Okay, so I post those practice one. There's going to be a take-home one, a review. We do the review before the test, and the test would be as we did it for the other one. It's going to be on Zoom. Okay, just make sure don't miss it. Have a good one. Take care. Bye-bye.